Take a deep breath in, letting the cool air fill your lungs, and as you exhale, allow your body to settle completely into the soft comfort of your bed. We are leaving the gravity of Earth behind tonight, joining a silent, tireless traveler in the dark. On September 5th, 1977, a machine weighing exactly 722 kilograms, just under 1,600 pounds, lifted off from a launch pad in Florida, tearing through the Earth's atmosphere on a trajectory aimed at the stars. This is Voyager 1. Within the first few moments of our journey together, we must orient ourselves to where this extraordinary craft is right now. Consider this. Voyager 1 is currently over 15 billion miles away from the very room you are resting in. It is an unfathomable distance, a stretch of cosmic ocean so vast that the human mind can only approach it by surrendering to its scale. Imagine the sensation of that distance. It is not an empty void, but a quiet, deeply peaceful expanse where the frantic pace of earthly life simply cannot exist. To maintain its outward push, Voyager 1 is traveling at approximately 38,000 miles per hour, which translates to an incredible 17 kilometers every single second. Yet, out here, in the deep interstellar medium, there is no friction to tear at its metal skin. There is no rushing wind, no turbulence, and no resistance. At 17 kilometers per second, the journey feels entirely motionless. If you were riding alongside this elegant machine, you would not feel the speed at all. You would feel only the profound, steady calm of floating, cradled by the invisible geometry of space. Let your mind trace the physical shape of Voyager 1 in the dark. It is a beautiful piece of mid-20th century engineering, dominated by a large pale dish. This is the high-gain antenna, measuring 3.7 meters, or about 12 feet, across. Picture the smooth parabolic curve of its aluminum frame, designed to catch the faintest whispers of radio waves from home. The texture of this metal is frozen in a way we cannot experience on Earth. The ambient temperature of deep space surrounding the probe is exactly 2.7 Kelvin. That is minus 455 degrees Fahrenheit, a temperature so perfectly cold that atomic motion slows to an absolute crawl. It is a deep, crisp, preserving chill that guards the spacecraft from the ravages of time. Yet, Voyager 1 is not entirely cold. It possesses its own internal warmth, a quiet, glowing heartbeat in the endless night. You might wonder how a machine survives in such freezing isolation. It is powered by 3 radioisotope thermoelectric generators, often called RTGs. Tucked safely in their metallic housings, these generators rely on the natural, steady decay of plutonium-238. Imagine the feeling of a small, radiant hearth fire. The plutonium-238 breaks down, atom by atom, releasing a gentle, continuous thermal energy that warms the delicate instruments aboard. This specific isotope has a half-life of 87.7 years. This means that year after year, decade after decade, the heat it provides slowly, gracefully dims. It is a soft, fading ember, keeping the spacecraft's core just warm enough to think, just warm enough to remember its mission. Feel the contrast of that gentle nuclear warmth radiating against the absolute minus 455-degree freeze of the vacuum. It is a cozy, protected bubble of heat sailing through the cosmos. Beneath that warm shielding lies the mind of the spacecraft. It is an incredibly humble intelligence by today's standards. The onboard computers of Voyager 1 possess just 69.63 kilobytes of total memory capacity, Think of the simplest digital file you own, a single text document or a tiny image, and realize that Voyager's entire memory is smaller than that. Its processor hums along, executing about 8,000 instructions per second. While modern technology measures calculations in the billions per second, Voyager operates at a slow, methodical, and deeply relaxed pace. It takes its time. It does not rush. Data is gathered and carefully spooled onto an 8-track digital magnetic tape recorder. In the pure silence of space, if you could press your ear to the metal chassis, you might feel the tiny rhythmic vibrations, the click and whir of magnetic tape spinning, physically recording the secrets of the universe, a mechanical heartbeat pulsing in the dark. But Voyager 1 carries something far more precious than just scientific instruments. Fastened securely to the spacecraft's exterior is a message. Imagine reaching out and running your fingers over the surface of the golden record. It is a 12-inch phonograph disc made of solid copper and richly plated in pure gold. The gold serves a vital purpose. It prevents the copper from tarnishing or degrading as it weathers the cosmic rays over millennia. The metallic surface is perfectly smooth in some places and intricately grooved in others. Even the protective cover of this golden artifact is a masterpiece of science and sensory memory. The cover has been electroplated with an ultra-pure sample of the isotope uranium-238. This was not done for power, but for timekeeping. Uranium-238 has a staggering half-life of 4.468 billion years, a number that perfectly matches the age of our home planet, Earth. It is a radioactive clock. If, in the unimaginably distant future, another intelligence finds this drifting golden disk, they can measure the remaining uranium, feel the slow ticking of its atomic decay, and calculate exactly how long ago Voyager was launched. Pressed into the golden grooves of this copper disk are the sensory memories of a world entirely unlike the void it now travels through. Encoded within its tracks are exactly 115 analog images. If translated back into light, they show the blues of our oceans, the greens of our forests, the structure of our DNA, and the faces of our ancestors. There are spoken greetings recorded in 55 different human languages, starting with ancient Sumerian, echoing the warmth of human voices across a space where sound cannot travel. There is one recording on the disc that is particularly intimate. It is an audio recording of human brainwaves. In the summer of 1977, a writer named Anne Druyan was attached to an electroencephalogram, an EEG machine. For an hour, she mediated on the beauty of Earth, the history of civilization, and the feeling of falling deeply in love. The electrical impulses of her brain, her heart rate, and her nervous system were translated into sound, compressed into a single dense minute of audio, and etched into the gold. Out there, 15 billion miles away, the physical sensation of human thought, of human love and peace, is frozen in pure copper. It rides the silent waves of the interstellar ocean, a perfect memory of warmth cast into the deep freeze of the universe. Voyager 1 is no longer in our solar neighborhood. On August 25, 2012, this quiet traveler achieved something profound. It officially crossed the heliopause. The heliopause is an invisible, majestic boundary in space. For billions of miles, the sun exhales a continuous stream of charged particles, known as the solar wind, creating a massive magnetic bubble called the heliosphere. This bubble cushions our entire solar system. But at the heliopause, the pressure of the solar wind finally gives way to the pressure of the interstellar medium. the ancient drifting gases that occupy the space between the stars. Imagine stepping out of a warm, slightly breezy room into a vast, utterly still, and crisp winter night. That is what Voyager 1 did. When it crossed the heliopause, its delicate instruments felt the change. It detected a sudden dramatic spike in plasma density. Inside the sun's protective bubble, the plasma was thin, measuring about 0.002 electrons per cubic centimeter. But the moment it pushed through the boundary into the great unknown, the density of those ancient particles jumped to 0.08 electrons per cubic centimeter. The environment became thicker, older, and deeply tranquil. The influence of our sun, the warmth, the magnetic wind, was left behind. Voyager 1 had entered the true, undisturbed ocean of the Milky Way. Because of this immense distance, communication with our golden traveler requires an exercise in extreme patience. When the giant radio dishes on Earth whisper a command to Voyager 1, the signal travels outward at the absolute speed of light, 186,000 miles every single second. Yet, the void is so deep that this signal, racing faster than anything else in the universe, takes over 22.5 hours just to reach the spacecraft, and it takes another 22.5 hours for Voyager's faint, one-way reply to wash back over the Earth. A single conversation takes nearly 2 days. It is a slow, rhythmic breathing across the cosmos. An inhale of data, a long pause of waiting, and a peaceful exhale of confirmation. As you lie there, feeling the weight of your body supported by your bed, let yourself sink into the rhythm of that 45-hour cosmic breath. Feel the slow, methodical turning of the tape recorders, the gentle fading warmth of the plutonium core, and the smooth, golden touch of a copper record carrying the sound of a human heartbeat. You are moving with it, coasting effortlessly at 17 kilometers a second, leaving the familiar behind, drifting out into the profound, comforting silence of the interstellar sea. There is no urgency here. There is only the long, quiet drift, the slow ticking of uranium clocks, and the magnificent peace of the deep unknown. The silent outward trajectory we are tracing together did not happen by chance. It was the result of a rare, perfect synchronization of celestial clockwork. In 1965, an aerospace engineer named Gary Flandreau made a groundbreaking observation while working at the Jet Propulsion Laboratory. He mathematically mapped the orbits of the outer planets, Jupiter, Saturn, Uranus, and Neptune, and discovered an impending geometric alignment. This specific, sequential arrangement of massive planetary bodies occurs only once every 176 years. This 176-year cycle is an incredibly rare cosmic window, a temporary alignment of the universe's heavyweights that allowed a single fragile machine to visit multiple distant worlds in one continuous arc, saving decades of travel time and immense amounts of fuel. To achieve this extraordinary journey, Voyager relied on an elegant technique mathematically proven by Michael Minovich in 1961, known as a gravity assist. Picture gravity not merely as a downward pull, but as a fluid, spinning current wrapped around a massive planet. A gravity assist acts much like catching the outstretched hand of a rapidly spinning dancer on a grand ballroom floor. As the spacecraft approaches the planet, it enters this invisible, swirling current, briefly merging with the planet's own orbital momentum. The spacecraft is then whipped outward at a drastically higher velocity. The planet loses a microscopic, entirely unnoticeable fraction of its orbital energy, and the spacecraft steals that momentum, gaining years of free travel time in the process. On March 5, 1979, Voyager 1 slipped into the immense gravitational embrace of Jupiter. At its closest approach, the probe glided exactly 217,000 miles above the gas giant's turbulent, swirling cloud tops, capturing incredibly detailed images of atmospheric bands tinted with deep reds, pale yellows, and crisp whites from crystallized ammonia. We must pause to contextualize this moment in human history. Centuries before this encounter, in the winter of 1610, the astronomer Galileo Galilei peered upward through a rudimentary telescope equipped with only a 20 times magnification lens. He saw Jupiter's largest moons as nothing more than faint, dancing pinpricks of pale light against the black glass of space. For over 360 years, humanity understood those distant moons only as blurry dots orbiting a larger sphere. Voyager 1 transformed those ancient pinpricks into complex, violently geological realities. What scientists discovered in the photographic data completely rewrote our understanding of planetary physics. On March 9, 1979, a navigation engineer named Linda Morabito was analyzing a routine photograph of Jupiter's moon, Io, to help confirm the spacecraft's exact position. Deep within the frame, she spotted a faint, umbrella-shaped anomaly rising from the edge of the moon. It was a volcanic plume erupting 190 miles high into the freezing blackness of space. Io, it turns out, is the most volcanically active body in our entire solar system. This constant, furious eruption is driven by a phenomenon called tidal heating. Jupiter's immense mass exerts such an intense, uneven gravitational pull on Io that it physically kneads the moon's interior like heavy clay. As the moon travels along its slightly elliptical orbit, solid rock on Io's surface bulges upward and falls downward by as much as 330 feet. Notice how gravity, at this scale, is not just a gentle tether. It is a profound physical force that bends rock and generates deep internal friction. It is a world endlessly expanding and contracting, breathing with molten heat under the cold vacuum. By successfully stealing momentum from Jupiter's massive gravity well, Voyager 1 gained a staggering speed boost of 35,700 miles per hour. This elegant orbital ballet hurled it seamlessly toward its next massive target, Saturn, achieving its closest approach on November 12, 1980. The probe flew silently within 77,000 miles of the ringed giant, analyzing the intricate icy debris of the rings in unprecedented detail. Here, the history of astronomy echoes once again across the centuries. Back in 1655, the Dutch astronomer Christian Huygens discovered Saturn's largest moon, Titan. Through his long tubular telescope, it appeared merely as a pale, featureless orange orb circling the magnificent rings. When Voyager 1 approached this mysterious moon centuries later, its specialized instruments revealed a world veiled entirely in a dense, opaque, nitrogen-rich haze. The telemetry beamed back across millions of miles confirmed that Titan's surface atmospheric pressure is 1.45 times greater than Earth's at sea level. It is a heavy, thick environment, completely impenetrable to visible light, hiding entire lakes and rivers of liquid methane beneath its amber-colored clouds. To study this uniquely thick atmosphere closely, mission planners made a deliberate and profound sacrifice. They programmed the spacecraft to dive below Titan's south pole, passing at a remarkably close distance of just 2,500 miles. This precise, calculated maneuver acted like a sharp, sudden bend in a flowing river. The gravitational tug of Titan permanently altered Voyager's trajectory, pulling it forcefully away from the flat, two-dimensional orbital plane where the planets of our solar system reside. It was flung sharply upward, exiting the solar system's ecliptic plane at an angle of 35 degrees. Because of this steep 35-degree upward trajectory, the spacecraft could never again cross paths with another planet. The remaining giants, Uranus and Neptune, as well as the dwarf planet Pluto, were permanently out of reach, left for its sister ship, Voyager 2, to explore. But this intentional sacrifice granted Voyager 1 its current, deeply solitary path into the uncharted cosmos. What's happening now is a quiet, eternal glide toward the northern constellation of Ophiuchus. While it will not encounter another physical star system for a time frame almost beyond our comprehension, its path is gracefully set. Scientists calculate that in exactly 38,000 years, this silent, golden-plated machine will pass within 1.6 light-years of an obscure red dwarf star known as Gliese 445. It is a journey defined by an extraordinary measure of patience. 38 millennia from now, Earth will have changed in ways we cannot predict, yet this small piece of human engineering will still be coasting, untouched and perfectly preserved through the freezing void. Reflect quietly on that immense timeline. As humanity evolved from grinding and polishing small glass lenses by candlelight in the 17th century to launching nuclear-warmed sensors across the solar system in the 20th century, the fundamental laws of motion remained beautifully, reassuringly constant. The slow, predictable clockwork of gravity governs both the falling of an autumn leaf on Earth and the multi-century voyage of a metal emissary through the stars. Permit your thoughts to rest comfortably in that certainty. The trajectory is fixed. The mathematics are perfect. The universe operates on an endless, deeply rhythmic schedule, turning in the dark, asking absolutely nothing of you, but to observe its quiet magnificence. Picture this elegant machine sailing perfectly steady through the velvet darkness. Long before it crossed into the uncharted interstellar sea, Voyager 1 paused to look back toward the home it would never see again. On February 14, 1990, when the spacecraft had traveled exactly 3.7 billion miles, or roughly 6 billion kilometers, away from our sun, an unprecedented sequence was initiated. At the request of astronomer Carl Sagan, mission controllers beamed a command instructing the probe to turn its cameras around and capture a final family portrait of our solar system. The spacecraft methodically snapped 60 individual frames, preserving a mosaic of the planets from a vantage point no human eye had ever reached. In one specific frame, caught suspended within a scattered ray of sunlight that had bounced off the camera's internal optics, sits a tiny pale blue dot. That is Earth. In the raw data beamed back to the waiting receivers, our entire world occupies a mere 0.12 pixels in size. Allow your mind to rest on that incredibly small number. Think of a single microscopic speck of dust floating peacefully in a warm sunbeam, filtering through your bedroom window. From 3.7 billion miles away, all of human history, every ocean, and every mountain, and every resting mind is contained within that fraction of a single pixel. It is a profoundly comforting perspective, gently reminding us that our daily worries are infinitely small when placed against the quiet, majestic tapestry of the cosmos. Consider the everyday objects around your home to truly grasp the quiet mechanics of this solitary traveler. The radio transmitter on Voyager 1 radiates at a power level of exactly 22.4 watts. If you open your refrigerator in the middle of the night, the small, soft light bulb illuminating the shelves typically uses about 15 to 40 watts. That means this distant spacecraft is projecting its voice across billions of miles of empty space, using the same amount of energy as a small, humble household light bulb. As those radio waves travel outward from the probe, expanding and stretching through the immense quiet theater of space, their energy naturally dissipates over the long journey. What's happening now is that by the time Voyager's signal washes over our planet, its power has diminished to a fraction of a billionth of a watt. Physicists call this incredibly tiny measurement an attowatt, represented mathematically as 10 to the negative 18 watts. To comprehend a signal this astonishingly faint, imagine dropping a single delicate snowflake onto the frozen surface of a vast lake. The microscopic energy of that snowflake landing is immense compared to the whisper of data Voyager sends. Deep within the high deserts of California, the mountains of Spain, and the valleys of Australia, humanity listens for this snowflake. The Deep Space Network utilizes massive parabolic dish antennas, measuring an astonishing 70 meters, or 230 feet, across. They are silvery, sweeping bowls turned skyward, patiently catching the invisible ripples of telemetry. To prevent the natural vibrating heat of the electronics from drowning out Voyager's microscopic whisper, the amplifiers at the core of these massive antennas are bathed in liquid helium. This cryogenic fluid cools the receiving instruments to a profound minus 452 degrees Fahrenheit, or minus 269 degrees Celsius. This supercooled state eliminates thermal noise, creating an electronic silence so absolute that the earthbound computers can hear a 22-watt light bulb murmuring from 15 billion miles away. Notice how the physical structure of Voyager 1 is designed with this same need for pure, undisturbed clarity. Extending away from the main chassis of the spacecraft is a slender, fragile-looking structure known as the magnetometer boom. It is made of lightweight fiberglass and measures exactly 13 meters, or 43 feet, in length. The sensors attached to the very tip of this long arm are designed to measure the faint magnetic fields of the galaxy. If these sensitive instruments were placed too close to the spacecraft's central computers, the subtle electronic hum of the machinery would interfere with the readings. It is identical to holding a sensitive hiking compass as far out at arm's length as possible, ensuring that the metal zipper on your jacket or the buckle on your belt does not skew the magnetic needle. By holding its sensors 43 feet away, Voyager ensures its perception of the surrounding galaxy remains flawlessly pure and perfectly balanced. At this very moment, the environment gliding past those extended sensors is known as the interstellar medium. It is easy to imagine the space between the stars as completely empty, a total vacuum, but that is not mathematically true. The interstellar medium is a highly refined, ancient mixture, composed of approximately 99% gas and 1% incredibly fine dust. The gas is predominantly hydrogen, the oldest and most abundant element in the universe, gently mixed with traces of helium. It forms an invisible, sprawling mist. The density is phenomenally low, often holding just one atom in an area the size of a sugar cube, but it is there. A serene, slowly drifting fog of raw stardust, quietly waiting through the eons to eventually collapse and ignite into new suns. Scientists discovered that to maintain its precise orientation as it sails through this gentle hydrogen fog, Voyager relies on a system of tiny, flawlessly engineered thrusters fueled by liquid hydrazine. For the main antenna to continue pointing directly at our pale blue dot, the spacecraft must not tumble or drift. Over the decades, the primary thrusters used to adjust the spacecraft's posture began to naturally degrade. So, In late 2017, mission engineers decided to attempt something extraordinary. They sent a command to awaken a backup set of thrusters, known as the Trajectory Correction Maneuver thrusters, which had been resting completely dormant, asleep in the freezing dark, for 37 years. With incredible precision, the hydrazine flowed. The catalyst beds warmed, and the backup thrusters fired perfectly. They provide thrust in micropulses lasting mere milliseconds. Imagine the softest puff of breath from pursed lips, just enough air to gently nudge a floating dandelion seed without causing it to spin out of control. That is the exact level of force used to steer a 1,600-pound machine 15 billion miles away. It is a slow, rhythmic correction. A millisecond puff of nitrogen gas, a subtle adjustment of mass, and the giant dish is once again perfectly aligned with home. It is like a sleeping person, subconsciously shifting their weight beneath the blankets, finding a state of perfect balanced comfort without ever waking up. We must look softly ahead, tracing the invisible line Voyager 1 will follow in the centuries to come. The spacecraft is currently speeding toward a colossal, spherical shell of icy debris that completely surrounds our solar system, an ancient structure known as the Oort cloud. This boundary is so phenomenally distant that even traveling at 17 kilometers every second, it will take Voyager approximately 300 years just to reach the inner edge of this celestial sphere. The Oort cloud is composed of billions, perhaps trillions, of dormant comet nuclei, silent mountains of frozen water, solid ammonia, and crystallized methane. You might imagine them clustered tightly together, but the reality of space is far more expansive and serene. These icy sentinels are separated by tens of millions of miles. It is like walking through a mist of morning dew, where each tiny droplet of water is suspended a mile apart from the next. The spacecraft will glide right through this sparse frozen mist without touching a single piece of debris. It will take Voyager 1 an estimated 30,000 years to traverse the entire thickness of the Oort cloud and finally emerge from the outermost gravitational influence of our sun. 30,000 years of quiet, uninterrupted gliding. Invite your breathing to match the magnificent, unhurried pace of that journey. Decades turn into centuries, centuries dissolve into millennia, and still, this golden emissary will be coasting forward, held safe in the preserving chill of the void. There are no sudden changes out here. There are no loud disruptions. There is only the steady, comforting progression of physics, a perfectly choreographed glide through the ancient gases and sleeping ice of the deep cosmos. As we travel further into this quiet corridor of deep space, suspended flawlessly in the comforting dark, we must acknowledge the delicate mechanics keeping our silent traveler oriented. Without the familiar pull of a planetary orbit or the guiding warmth of the sun, you might wonder how a machine maintains its bearings in an endless, multi-directional void. The answer lies in finding a reliable anchor, much like the steady, rhythmic breath you rely upon to center your own mind at the end of a long day. Observe how Voyager 1 navigates. It utilizes a highly sensitive piece of optical equipment called a star tracker. For decades, this unblinking electronic eye has remained permanently locked onto Canopus. Canopus is a brilliant, golden-white supergiant and is officially the second brightest star in the Earth's night sky, located in the southern constellation of Carina. By keeping this specific luminous beacon continuously in its sights, the spacecraft's attitude control system perfectly maintains its pitch and yaw. It is a beautiful parallel to the human experience. When navigating through the uncertainties of our own lives, we intuitively seek a fixed point of light, a memory, a loved one, or a profound hope to keep us steady when the environment around us goes dark. Deep within the structural core of the spacecraft, another deeply familiar process is unfolding. It is the graceful art of conserving energy. As you lie resting, your biological systems are intelligently powering down. Your core body temperature drops by a fraction of a degree. Your heart rate slows to a tranquil rhythm, ERI, and energy is diverted away from active muscles to focus purely on preservation and healing. Voyager 1 mimics this biological sleep cycle with absolute precision. Because its nuclear power source naturally decays, the total electrical power output of the spacecraft decreases by approximately 4 watts every single year. To ensure the most vital communication systems survive as long as possible, mission controllers systematically command the spacecraft to shut down non-essential functions. In 2011, engineers executed a remote command to turn off the heating elements that were keeping the ultraviolet spectrometer warm. Without its dedicated heater, researchers noted an extraordinary drop in temperature. The instrument plunged into the freezing dark, stabilizing at minus 79 degrees Celsius, which is minus 110 degrees Fahrenheit. The astonishing reality is that this delicate spectrometer was only originally tested to withstand a lower limit of minus 35 degrees Celsius. Yet, in that extreme, unimaginable cold, the instrument did not shatter or fail. It simply adapted to the deep freeze and continued to operate, proving the incredible enduring resilience engineered into its very frame. At this very hour, the environment surrounding those chilled instruments is not entirely silent. While the vacuum of space cannot carry acoustic sound waves like the air in your bedroom does, it carries something equally profound. The probe is equipped with the plasma wave subsystem, an instrument designed to detect the electrical field components of local plasma waves. In 2012, and again in 2014, this sensitive electronic ear recorded a phenomenon known as electron plasma oscillations. When solar flares from our distant sun occasionally collide with the ancient, drifting interstellar plasma, the collision causes the invisible charged particles to ring like a struck bell. The instrument translated these electrical vibrations into an audible frequency range between 2 and 3 kilohertz. If you were to hear it, it would sound like a pure, eerie, and gently rising whistle echoing through an empty hall. The pitch of this electronic song corresponds directly to the density of the plasma. A higher pitch indicates a higher density of surrounding particles. It is the literal music of the cosmos, a slow harmonic vibration sweeping across billions of miles. You're playing a song that has existed long before humanity first looked up at the night sky. There is another, far more deliberate piece of music bolted to the side of the spacecraft, waiting in the dark. We must look closely at the golden record once more, not just at its golden hue, but at the precise mechanics required to decode its message. The mission planners knew that whatever intelligence might find this artifact would need the tools to comprehend it. Therefore, securely mounted to the exterior, right beside the record itself, is a stylus and a specialized playback cartridge. Engraved directly onto the protective aluminum cover are symbolic instructions for how to use this stylus, written in the universal language of binary arithmetic. To explain the concept of time to an unknown listener, the creators needed a fundamental unit that exists everywhere in the universe. They chose the hydrogen atom. The diagrams indicate a time state based on the fundamental transition of a hydrogen atom, which takes exactly 0.70 billionths of a second. Using this infinitesimal universal heartbeat as a foundation, the binary code explains that the record must spin at a highly specific speed of 16 2/3 revolutions per minute to be heard correctly. Think of a grand ancient redwood tree that has stood in a silent forest for thousands of years. When you study a cross-section of its massive trunk, you find concentric rings tightly packed together. Each ring is a physical, tactile recording of a single year. A year of heavy rain, a year of drought, a year of gentle sunlight. The golden record is carved with the same beautiful, natural logic. It contains a single, continuous micro-grooved spiral, a man-made tree ring that holds exactly 90 minutes of human music, waiting for a needle to trace its physical valleys and peaks. Stored within those microscopic valleys is a deeply personal legacy, a testament to the immense diversity of the human experience. Included in this 90-minute symphony is an audio recording of a pygmy girl's initiation song from the Ituri forest in Zaire, originally captured on tape by the anthropologist Colin Turnbull. It is a rhythmic, joyous, echoing chorus of human voices, celebrating the passage of time and the bonds of community. Following it in the quiet rotation of the disc is a beautifully complex Chinese musical piece known as Flowing Streams. This specific piece of music is over 2,500 years old. It is performed on a traditional 7-stringed instrument called a guqin. Permit your thoughts to linger on the sound of a silk string being plucked. The vibration of that ancient instrument, echoing a melody composed millennia ago on the muddy banks of a terrestrial river, is now frozen in solid copper. It is sailing at 38,000 miles per hour through a freezing hydrogen fog, destined to outlive the very mountains from which its wooden body was carved. There is an immense, profound comfort to be found in this bigger picture. Our daily anxieties, the rapid pace of modern life, and the heavy burdens we carry in our waking hours are completely absent out here. The frantic ticking of clocks on Earth does not apply to the slow, majestic glide of Voyager 1. The spacecraft travels through an arena where thousands of years pass without a single collision, where the only changes are the slow decay of plutonium atoms and the gentle ringing of invisible plasma. As you settle deeper into your resting space, align your own heartbeat with the enduring journey of this golden artifact. It carries our songs, our ancient melodies, and the electrical imprint of our thoughts, keeping them perfectly safe in the ultimate vault of the universe. It asks for nothing in return. It does not demand attention or require us to hurry. It simply coasts onward, relying on its solitary star tracker to hold a steady gaze on a distant light, trusting in the unbreakable laws of physics to carry it through the peaceful, endless dark. Allow your mind to release its earthly tethers, borrowing the absolute weightlessness of that quiet, immortal flight. Progressing steadily along this ancient gulf, our solitary traveler passes invisible milestones. To fully map this leg of the voyage, scientists measure distance not in miles, but in astronomical units, or AU. One single astronomical unit represents the exact distance between the Earth and our Sun, roughly 93 million miles. At this current stage of its flight, Voyager 1 is traversing a region over 162 astronomical units away from the center of our solar system. That means you could line up the distance from the Earth to the Sun 162 times, end to end, to reach the exact coordinates where the probe sails tonight. Observe carefully the texture of this environment. It is profoundly quiet, yet it is not entirely empty. The interstellar medium is scattered with microscopic grains of silicate dust. These floating particles are so vanishingly small that their mass is typically less than 1/1,000,000,000 of a gram. Because the density of this cosmic dust is so incredibly low, a physical impact on the spacecraft's outer hull occurs roughly only once every few days. When one of these infinitesimal grains does strike the metal, there is no sound, just a microscopic transfer of kinetic energy easily absorbed by the shielding. Have you ever wondered what this specific region of the galaxy might smell like if human senses could safely process the vacuum? Astrochemical analysis of the interstellar medium reveals the presence of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. These molecules were forged eons ago in the thermal furnaces of dying red giant stars and cast out into the cold. If you were to gather enough of these PAHs into a breathable atmosphere on Earth, they would carry a distinct, sharp olfactory profile, resembling the scent of charred charcoal, burnt toast, or lingering welding fumes. It is the smoky metallic perfume of ancient stellar decay, suspended forever in the deep freeze. To survive flying through this ancient chemistry, Voyager 1 is draped in highly specialized thermal blankets. You have likely seen photographs of the probe, noting its iconic, crinkly gold and silver foil appearance. This material is not simple metal. It is a specialized polymer called Kapton polyimide film. The spacecraft is wrapped meticulously in 15 alternating layers of this Kapton, with each individual sheet coated in a microscopic layer of aluminum. The scientific reason for this golden armor is elegant. It is designed specifically to trap infrared radiation. As the internal plutonium power source generates heat, those thermal waves attempt to radiate outward into the freezing vacuum. The 15 layers of aluminum-coated Kapton act as a perfect mirror, reflecting the infrared heat right back into the core of the chassis, keeping the delicate computers functioning. On Earth, this Kapton material feels crisp and crinkly to the touch, much like a stiff cellophane wrapper. But out here, exposed to the ambient temperature of deep space, the polymer has become absolutely rigid. Its wrinkles and folds are permanently frozen, preserving the exact handprints and creases left by the aerospace technicians who wrapped it over 4 decades ago. Deep in the architecture of the cosmos, there are colors waiting in the dark that the human eye cannot naturally perceive. To our biological vision, the space surrounding the Kapton foil is pitch black. Yet, the physics of the sparse hydrogen gas drifting past the spacecraft tells a different story. Occasionally, a wandering electron within a hydrogen atom will naturally drop from a higher energy state down to a lower one. When it makes this tiny quantum leap, it must release energy in the form of a photon. Because of the specific atomic structure of hydrogen, this emitted photon always travels at exactly 656.28 nanometers. In the spectrum of visible light, 656.28 nanometers translates to a faint, deeply saturated red hue, a phenomenon scientists call H-alpha emission. If your eyes were sensitive enough to capture these single glowing photons over long exposure times, the seemingly black void around Voyager would actually appear as a soft, sprawling watercolor wash of deep crimson. It is a warm, hidden color palette painted across the coldest canvas imaginable. To study this complex environment, the spacecraft relies on a suite of sensory instruments, each with its own mechanical heartbeat. One of the most fascinating is the low-energy charged particle instrument, or LECP. To measure particles arriving from all possible directions, the sensors inside the LECP cannot remain stationary. They must look around. To achieve this, engineers installed a tiny stepping motor designed to physically rotate a heavy shield back and forth by exactly 45 degrees. Think of a patient lighthouse beacon, methodically sweeping its heavy glass lens back and forth across a dark ocean. The stepping motor on the LECP works with that same rhythmic, tireless dedication. Before launch, the engineers on Earth stress-tested this tiny mechanical joint, hoping it might endure roughly 500,000 rotations. Today, floating billions of miles away, this small, clicking motor has successfully executed over 7 million mechanical steps. Every few hours, it perfectly rotates 45 degrees, pauses to collect data, and rotates back. In the absolute silence of the vacuum, the subtle physical click of that motor engaging is a testament to the enduring perfection of human engineering. What the LECP and its sister instrument, the cosmic ray subsystem, are looking for are fragments of destroyed stars. The cosmic ray subsystem is specifically calibrated to detect atomic nuclei that have been violently stripped entirely of their orbiting electrons. These naked, high-energy particles are known as galactic cosmic rays. They originate from the massive, explosive shock waves of ancient supernovae, occurring thousands of light years away. Because of the immense force of those distant explosions, these cosmic rays are propelled through the galaxy at astonishing velocities, reaching roughly 99% the speed of light. Yet, as they strike Voyager's sensors, there is no chaos. The sensors record a steady, predictable average of about 2 to 3 high-energy impacts every single second. Imagine sitting comfortably inside a sturdy cabin, listening to the slow, rhythmic tapping of heavy raindrops hitting a tin roof. 2 or 3 gentle taps every second. That is the exact rhythm of supernova remnants arriving at the spacecraft, a quiet cosmic drumming echoing from the death of stars. Scientists back on Earth must monitor exactly how fast Voyager is coasting as it absorbs these atomic raindrops. To calculate a velocity with flawless precision from 15 billion miles away, navigators utilize the Doppler effect. The spacecraft transmits its engineering data using an 8.4 gigahertz radio frequency, operating on what is known as the X-band of the electromagnetic spectrum. Because the probe is constantly moving away from Earth, the invisible radio waves it broadcasts are physically stretched out over the distance. It is exactly the same acoustic principle you experience when listening to the heavy horn of a freight train as it rushes past you and fades away into the night. As the train recedes, the sound waves stretch, and the pitch of the horn drops lower and lower. The massive radio dishes on Earth listen for this exact stretching in the 8.4 gigahertz X-band frequency. By mathematically calculating how far the radio waveform has elongated, navigators can determine Voyager 1's exact speed down to a fraction of a millimeter per second. There is no guesswork. There is only the crisp, immaculate certainty of mathematics. The radio wave stretches, the numbers align, and the speed is perfectly known. Permit your physical form to sink deeply into the comfort of your resting place, guided by the flawless reliability of these physical laws. And the universe is not a place of random chaos. It is a beautifully orchestrated system of cause and effect. Electrons drop in energy, releasing red photons. Supernovae collapse, sending rhythmic cosmic rays across the dark. A tiny mechanical motor steps 45 degrees with tireless precision, and the invisible stretching of an X-band frequency connects a quiet golden machine back to the minds that built it. Invite the sensation of that magnificent order to wash over your thoughts. Everything out here functions exactly as it should, moving with a calm, deliberate purpose through the ancient charcoal-scented mist of the Milky Way. Observe the gradual, inevitable winding down of our magnificent traveler. As we watch the timeline unfold into the future, The voyage of this golden emissary approaches a quiet, beautiful transition. We are witnessing a meticulous process of conservation, a step-by-step surrender to the absolute peace of the deep cosmos. Trace the sequence of its remaining energy. At this moment, Voyager 1 operates on a strictly managed power budget of roughly 249 watts. This is a significant decrease from the 470 watts of electrical power it generated upon its launch from Earth in 1977. To delay the inevitable silencing of the spacecraft, mission engineers execute a highly choreographed procedure. One by one, non-essential systems are systematically powered down. The sequence is deliberate and unhurried. Sometime in the late 2020s or the early 2030s, this sequential shutdown will reach its final phase. The critical X-band radio transmitter, the voice of the spacecraft, requires exactly 23 watts of electricity to function. When the decaying plutonium core can no longer produce those final 23 watts, a permanent threshold will be crossed. The transmitter will gently power off. After more than half a century of continuous whispered conversation across billions of miles, Voyager 1 will enter a state of complete, unbroken radio silence. Following this ultimate shutdown, a profound physical transformation will begin. Without the internal warmth of active electronics, the spacecraft's core temperature will undergo a slow equalization process. Step by step, the heat will radiate away into the void until the metal chassis entirely matches the ambient temperature of the cosmic microwave background, a perfectly stable 2.7 Kelvin. In this frozen state, the machine achieves a form of mechanical immortality. Because there is absolutely zero free oxygen floating in the interstellar medium, the process of oxidation cannot occur. The aluminum and titanium structural struts will never rust, tarnish, or corrode. The only physical degradation will come from the extremely rare impacts of microscopic dust particles. Astrophysicists calculate that it will take approximately 1 billion years for these microscopic abrasive impacts to significantly smooth down the grooves carved into the copper face of the golden record. For 1 billion years, the music and the memories of Earth will remain physically intact, perfectly preserved in the dark. Without power, without commands from home, Voyager 1 does not stop. It merely shifts its role from an active observer to a silent, eternal monument. It will continue moving at its current speed, entering a lonely, independent orbit around the supermassive black hole at the center of the Milky Way. It takes our home galaxy roughly 225 million to 250 million Earth years to complete one single, majestic rotation. Our golden time capsule will trace this immense circular path, coasting silently toward the northern constellation of Camelopardalis, the giraffe. It will drift through the ancient gases, circling the galactic core alongside the stars for eons. Reflect on this magnificent unbroken connection between the distant stars and the very bed you rest upon tonight. The ancient stellar environments Voyager navigates are the exact boundaries that constructed you. This is not a poetic metaphor. It is a verifiable step-by-step physical process known as stellar nucleosynthesis. For millions of years, deep within the crushing gravity of a massive star, a methodical sequence of nuclear fusion takes place. Hydrogen atoms are fused into helium. As the temperature incrementally rises, helium is compressed into carbon, and carbon is ultimately forged into oxygen. Consider that oxygen, created in the belly of an ancient sun, makes up exactly 65% of your total body mass. Every time your chest rises and falls, you are utilizing an element synthesized in the fires of deep space. As a massive star reaches the absolute end of its life cycle, its core temperature spikes dramatically, and a final frantic sequence begins. In the mere fraction of a single second before the star collapses, it fuses silicon into iron. The human body contains exactly 4 grams of this specific element, bound intimately within the hemoglobin molecules of your red blood cells. The iron coursing through your veins right now, carrying oxygen to your resting muscles, was forged in the terminal, split-second gasp of a dying star. When that star finally explodes in a magnificent supernova, it ejects these newly created heavy elements outward at staggering velocities, exceeding 10,000 kilometers per second. This explosive shockwave seeds the surrounding cosmic clouds with calcium, carbon, and iron. Over billions of years, those expelled elements slowly gathered, clumping together through the gentle rhythmic pull of gravity to form our sun, our planet, and ultimately, your physical form. The calcium fortifying your bones was born in a supernova shockwave. You are not separate from the quiet, dark space Voyager travels through. You are an intricate, breathing extension of it. As we bring this observation to a gentle, comforting halt, invite your biological systems to mirror the peaceful shutting down of our distant spacecraft. Transition from the vast external architecture of the galaxy to the intimate internal warmth of your own rest. Your body is undergoing its own sequential power-down procedure. The heart naturally decelerates, lowering its output to a tranquil, effortless rhythm. Your respiratory rate stabilizes, settling into a continuous, calming cycle of 12 to 20 breaths per minute. To initiate deep metabolic rest, your core body temperature intentionally decreases by precisely 1 to 2 degrees Fahrenheit. It is a biological power-saving mode, a flawless mechanical intelligence within your own cells, ensuring that you are preserved, healed, and restored. Inside the architecture of your mind, the rapid active frequencies of waking thought are slowly giving way. The cerebral cortex transitions into a state dominated by delta waves. These specific brain waves operate at a deeply resonant frequency of exactly 0.5 to 4 hertz. This slow, majestic rhythm of 0.5 to 4 hertz mathematically matches the extreme low-frequency hums found in the deep spaces between the stars. As you descend into sleep, your mind physically hums at the same slow frequency as the quiet, resting universe. You are perfectly safe. You are held by the same unbreakable forces of gravity that guide the planets and cradle the stars. There is no rush here. There is only the slow, steady turning of the Earth. Your breathing aligns with the silent, majestic rotation of the galaxy. The iron in your blood remembers the calm of the stars. The oxygen in your lungs grounds you in the present moment. Your temperature cools softly, wrapping you in absolute comfort. Every muscle surrenders its tension, floating weightlessly in the dark. The mind quiets its final transmissions. The thoughts slow down, mirroring a quiet machine coasting into the eternal night. You are made of stardust, returning to a state of perfect, undisturbed peace. Rest now in the comforting void. Sleep in the silence of the cosmos. Good night.